Do you have merch yet?
No merch.
Oh, come on. We got to cold open some merch.
We have virtual merch. We have Virch.
Yeah.
There we go.
Because some people in our community made a like yellow text on purple background generator, and you can kind of gen up a t-shirt with that.
We were making Brad and Will NFTs. They're trading cards. There's they're $99 each.
Some of the prizes include dinner with me. I don't know if that's a good prize, but it's what we have.
Play golf on one of our many golf courses. There's a picture of me riding a purple and gold elephant with no shirt on. I don't know why. What?
Man, how do you just get into NFTs now?
I really thought the merch should be just Brad's old monitors.
Those monitors have gone to the great beyond, unfortunately, at this point. I tried. I actually went on the Discord and said, hey, I'm about to e-cycle these monitors. Does anyone want them? No takers.
By e-cycle them, you mean you put them on a chair with a sign that said free outside your front door, right?
No, I scheduled actual e-waste pickup.
Wow. Well, they come pick it up?
I thought long and hard about it. I started to donate them.
Okay.
To like a Goodwill situation.
And even they said no. They were like, no, thank you.
I didn't actually try. I mean, I considered doing that. I considered going on Craigslist and saying like, hey, free monitors, just come pick them up. And then I thought about what's in those monitors and how old they are.
Yeah, there's a lot of guinea pig dust in there.
No, I mean like the cold cathode backlights. Like that's how old those monitors are, is that they're way, way pre-LED. And I thought like the amount of electricity these things use and the closeness to their death they probably are is actually just that's doing someone a disservice to make them take these monitors and use them, because they're going to suck up way too much power and they're going to die at any moment. Taking
them out of circulation was the right choice, I think.
I think you should have slapped a content.town sticker on them. And they should have been a Patreon reward tier.
Look, Kishore, I'm not going to lie. I looked up to see how much it would cost to get purple sweatpants with yellow Will and Brad slapped on the ass cheeks would cost. Unfortunately, it was too much. That's our hockey. That's the hockey jersey of this podcast.
I don't know if any price is too much for that.
The real question is, who goes on which cheek?
Well, Brad goes on left cheek and I go on right cheek. Clearly, it's Brad and Will. The and is in the middle. Welcome to Brad and Will Made a Tech Pod. I'm Will.
I'm Brad.
Joining us today is a very special guest and our dear friend, Kishore Hari. Welcome back to the show, Kishore.
I'm really excited to be here. Either this means the world is ending yet again, or there's a sale on bidets somewhere. Like those are the only two options for me appearing on this podcast.
Your bidet fluencer gig is starting to pick up, I've heard. So luckily, the world's not ending again. I didn't introduce you as our apocalypse consultant. So we're here to talk about science today, though. It's gonna be fun because I feel like we introduced you this before, but in case people don't know. Yeah, you are a professional science communicator. You tell people, you explain the science to the people in a way that is digestible and understandable and fair and just and conveys the important stuff without being sensational. Or I don't know. Am I doing a good job explaining?
I think you're really setting me up for failure, because this is I really wanted to talk at people instead of talk with. Now I feel like I have to be reasonable in my descriptions of science this year.
Oh, no. There's nothing reasonable about science. That's well established. So we're doing something a little bit different this week. We wanted to do kind of hey, here's the stuff that we thought was interesting in science this year. Like it's not necessarily like the biggest stories, but it's the stuff that we thought was cool, kind of across the board.
It's kind of a show and tell. Everybody picked a couple of stories from this year that were, let's say, inspiring.
Yeah.
I would say this is not the indie hits of science this year, because there were so many big science stories that I think caught our attention that we are playing the hits today. But there's a reason we're playing the hits, because the hits were amazing this year.
Yeah. And there's also like I looked at like mRNA impacting cancer vaccine. The work that went into the mRNA vaccines seems like it's going to completely change a lot of infectious disease stuff in the next like 3 to 5 years. But there was so much happening there, I kind of couldn't find one thing to pick, because it's like there were 50 little big things that came out this year about this. We're not going to talk about that just up front.
It's always hard to pick out science stories because I think we default to discovery as a way of selecting science stories. But I think we can all relate to the fact that science is incremental. There are all these mini progresses that happen that lead to this thing that we label as discovery, but it's really the agglomeration of all of that work together. So when you're talking about stuff like vaccine development or drug development or a myriad of other things in health or in numerous other scientific fields, like picking the point at which you say, like, this is a huge story is a little bit arbitrary. And so with that qualification, let's talk about some arbitrary stories that we found pretty interesting.
Honestly, my guiding principle here was, what did I find inspiring? What fired the imagination for me is kind of how I picked.
Should we start with the most beautiful story of the year then?
Yeah, I think so.
Which one? That could be multiple things.
I think we'll start with the Just Wonderful telescope, and which is what I encourage everyone else to call it for reasons. If you Google his name, you'll discover reasons why you should just call it the Just Wonderful telescope. And I'm going to start with a non-science element of what JWST brought us this year, and that's just pure beauty. I don't think it can be understated when I rewind the clock to the mid-90s. How impactful it was when I saw the Pillars of Creation photo from Hubble. Like, we all know, if we say the word Pillars of Creation, an image pops up in our head. And the meaning of those images to feeling the imagination and inspiration of people across the world, in addition to all the people that have talked about how those images encourage them to become astronomers and astrophysicists and the like, can't be understated. And there's so much that emerged from JWST this year that was just beautiful. Put aside the science for a second. My personal favorite is a spiral galaxy. It's NGC 628. There's imaged with the MIRI instrument, which is the mid-infrared instrument in the JWST. And it's a nearly perfectly symmetrical spiral galaxy. How does our universe make something so symmetrical at the scales that we're talking about here? And then there was the image that I have framed in my house is the zoom in of the Carina Nebula, which is a stellar nursery. And I just found like the overlay of the zoomed in part that JWST took of the Carina Nebula over the Hubble image. Just it still brings a tear to my eye thinking about the vastness that represents and the birth of stars and what I hope is the birth of life. And then there's the actual kind of science part. And I think the most important science to me that JWST brings about is its work on looking at atmospheric composition. And this year we saw the initial signs of what it can do. So it looked at, one planet it looked at, and it looks at this by looking at the light of the star shining through the atmosphere of this planet and kind of coming into the instrument. And from that, you can use a spectrometer to actually analyze the potential atomic composition. So it looked at a planet in the WASP 96 area, WASP 96b. This is a planet that's 0.48 the mass of Jupiter. But it's so close to its sun that it orbits it every 3.5 days.
Is it 3.5 day long year? Holy cow.
And so just imagine a planet that's about half the mass of Jupiter circling its star every 3.5 days. It's incredible. It's an incredibly hot planet. It's about 1,000 degrees. But they were able to image water in its atmosphere. Water that close. I mean, this star is not as hot as our sun, but it was able to image that. And then you can imagine what this unlocks. And just this weekend, as we're recording this, there was an astronomy conference where they started to unveil how they studied for about a week and a half planets in the TRAPPIST-1 system. This is a system that the Kepler telescope observed in 2017 and identified 7 planets around a star that's still cooler than the sun. It's about 39 light years away. all the planets in this system are closer in its orbit than Mercury is to our sun. So it's a really tight orbital structure, and they're all rocky planets. And because these planets are much smaller than the Jupiter-like planet that I talked about earlier, it's hard to kind of tease out the signal. But over the next few months, they're going to be like deeply analyzing that data, and they're already getting some atmospheric composition. So they looked at one of the planet that is closest to that star, and they found a significant amount of hydrogen in its atmosphere. We're really going to be looking at this over the next year and seeing like, what do we know about the atmospheric composition? And when we start to see water in a planet that's in the Goldilocks zone, what could that possibly mean?
The imagery, the like long distance imagery that's been dominating the news has been so prevalent. I had no idea that they were even using this telescope for planetary science. That's wild. I don't know a ton about like xenobiology. Is the presence of water still considered like the necessary precondition for life to emerge, or is it just considered like one of many? I mean, obviously there are like other liquids, other conditions, or is that still the holy grail?
It is one of many, but without water, we can't even have a starting conversation.
It's amazing. The images that strike me out of JWST, like when they've gone through and recreated or redone the deep field surveys, where 30 years ago, I guess they aimed Hubble at a small patch of what we thought was dark sky and just kept taking pictures there until there was a big composite of what looks like a 1,000 galaxies. And the deep fields of JWST are even more breathtaking than those images after 30 years of doing these. You'd think we wouldn't be surprised that there's just always more stars, always more galaxies, but yeah, here we are.
Do you think there's potential for the big number to go up again? I feel like it was like 20 years ago that it was like, oh, there are roughly 100 billion known galaxies, and now I think that number's up to like 2 trillion.
I'm not sure the number of galaxies matter, because like the thing that won't go up is I think we have a very good handle on the mass of the universe. So like these are all kind of rounding errors in the larger scheme of things. So yeah, maybe there's a little bit more visible light out there than what we think, but it still does not explain the giant gap we have in the mass of the universe versus what we are able to see and what is emitting light. So even if there is like a change like you're talking about, it's still an overall rounding error. I think it matters more to our psyche, knowing that the vastness of space is just incredible to behold.
Can we talk about dark energy now?
Wait,
okay.
Sorry. I know you have a great segue.
That was an amazing segue.
I'm sorry. Just table it for 2 seconds. Okay. I was going to ask one more question here. So like you're talking about the JWST being used to study known exoplanets. Do you know if it's also going to be employed in detecting more unknown exoplanets? Because I know, the existing methods, like what is it, kind of planetary transit across the star and studying wobble of star under gravitational influence, all that stuff. Like, do you think like new methods of finding more planets are going to emerge from this thing?
Yeah, I don't know. My hunch from talking to some astrophysics colleagues is because time on the telescope is so precious, because there's so many demands on it, that in the near term, most of the proposals they're accepting and areas they're going to point at are places that we've already imaged before. So don't expect JWST to be pointing at just unknown areas where it's just going to randomly find a transit, just because we have so many targets already to look at more deeply. Now, 4 or 5 years from now, 10 years from now, is that going to be the case? I don't know. That's a good question.
Will, we can move on. I would love to talk to whoever it is that administrates time on that thing. Who is the gatekeeper for who gets to use that thing and for how long?
Can't be a fun job.
Oh.
Well, I mean, typically they have a committee on stuff like that, right?
Yeah,
so it's like it's people review papers and judge based on the relative merits and what they think is going to be the outcome and or the haul. But yeah, it seems like a lot.
All right, dark energy. There's your segue.
Yeah, dark energy. Perfect segue. I learned about quintessence this year, which I didn't know about before. For people who aren't familiar, when Einstein came up with general relativity 100 years ago, he added this thing in called the cosmological constant because they felt like the universe should be static at that time, that neither expanding nor contracting, as it is, as it was, as it always will be. And then Hubble, a few years after that, discovered redshift and discovered that implied that the universe was expanding. And Einstein famously said that his biggest mistake was putting the cosmological constant, and the biggest mistake of his life was adding the cosmological constant. So he pulled it back out of general relativity, threw it in the trash. And then you fast forward 60, 70 years, and we were able to measure the distance to extremely distant supernova very precisely. And we found again that the universe is accelerating, not just expanding. So so we went from static to constantly getting bigger at the same rate to constantly getting bigger at a changing rate. And that implied the existence of dark energy, which is a force, like in a world where the universe is made up only of matter and nothing else. Then the universe would eventually crunch down into a single point where, an infinitely dense black hole, yada, yada. The dark energy is the thing that we use to balance out the sheet, to kind of make it seem as though so that there's something pushing out from the force of gravity that would be pulling all things together. I'm just watching Kishore and hoping that he continues nodding here, because as long as he continues nodding here, I know I'm doing okay. But the idea that the power, the force of the dark energy, which still frankly seems kind of bullshit to me, is constantly expanding, is constantly is changing strength over time, is really interesting. And these three folks, Cosmin Andre, Anna Iyas, I think, and Paul Steinhardt, did the math this year and on their quintessence theories. And if they're correct, the upshot is that there's a little less time than we expected before the universe begins to contract. Yeah,
well, I think there's been, my understanding is for the last several years, the thought was that it would never start to contract, that the acceleration would only continue and the universe would just expand forever. And that, I feel like that's gone back and forth at least once in our lifetime.
So we're arguing at a chalkboard right now. I want everyone to kind of put aside the idea that like physicists or astrophysicists are having like these heated debates about like, no, the universe will contract. And no, they're having math arguments at boards. Is what's going on. And Will's right. Dark energy is basically a huge unknown in a number of mathematical equations that explain an enormous part of the universe. And
but it's something we've never observed, right? We haven't observed it. We don't have experimental proof that exists. Yeah,
it's just an explanation, right? Or a fudge.
And like the thing that we should acknowledge is there's a thing called inflationary theory that explains like femtoseconds after the beginning of the universe, there's this rapid expansion of the universe that leads to all of these long-term consequences, including the continued acceleration, a part of the universe that like Saul Perlmutter and others received a Nobel Prize for from their work in the mid-90s, establishing that. Now, inflationary theory is just a theory. There's a number of experimental projects like BICEP 2 in the Antarctic that have tried to really confirm that in aspects of inflationary theory. And the three scientists you mentioned, they study inflationary theory and are trying to come up with explanations for pieces of that theory that don't kind of work. And this idea of quintessence is really saying like this cosmological constant. Like, there's no reason there's just this random constant for the universe. Like, there isn't like a pi for the universe. Like, what is this
Planck's constant where there's a number without which the atoms wouldn't congeal, right?
What is this constant represent? And quintessence is like an attempt to try to explain what that cosmological constant is. And if quintessence aligns with the theories that these three have put forth, then there's the possibility of the ramification of that could be that the universe contracts. Do you all know Katie Mack? She's a great astrophysicist. She was actually Paul Steinhardt's student. He was her thesis advisor, and she wrote a book called The End of Everything a couple years ago that goes into all of these theories, like whether we just have a continual expansion and the heat death of the universe where just all heat just sort of evaporates and then we're left with the black void of nothingness, some of these contraction theories, whether the Galra from Voltron come in and take quintessence and transform it into energy, as I believe is canon.
I missed that one in her book.
Yeah, that one's not. I don't remember that. It got cut by the editors. I don't understand.
Must have been in the pre-reads, the proofs.
But I think this argument is like, it's a decades long argument that we're seeing like continual, like incremental progress on. And the quintessence one is really, it's an interesting one. It's a little mind bending-y. And I think what becomes fascinating is as experiments come online to potentially explore elements that could give us hints and insights into this.
Yeah, and so it seems like I don't know what those experiments are. Like, are we looking? Is this like a Nancy Roman telescope situation? Is this, It could
be like Bicep 2 is one that is looking at like elements from early universe as well that would give us insight into inflationary theory. So yeah, there's a number of experiments. There will never be the experiment, from what I understand, to confirm this, but there are a series of experiments that might give us insight into early inflationary time that could give us some height. But I had a conversation with Brian Greene years ago, and he's like, we're reaching the edge where experimental physics, like the amount of energy that's required to explore some of these spaces with like accuracy and precision is just beyond our capability. We'd have to start building like things the size of solar systems or galaxies to explore this, to achieve the energy we need to look back. And that's just not possible. So in this way, it's an exploration of the mind as much as anything else.
Maybe this is how that perfectly spiral galaxy got built.
Do I understand right about inflationary theory that like the thought is that like very minor features of that very early expansion, like little nuances in the way matter was distributed, are what led to like a lot of the current structures we see, like the distribution of galaxies directly followed from like very minor variations?
Yeah, I am upset on the universe's behalf for what you called minor, because we're talking about things like where it's like the energy to break apart the bonds of atoms. Like we're talking about, like you're talking about minor changes in that kind of fundamental force. We're talking about energy soups of like magnitude that we can't really conceive of. It's just over a time scale that is so small that it's hard to conceive, is what I think is really challenging about it for how I picture it.
Femtoseconds. Fractions of femtoseconds.
And I'm sure I'm off by orders of magnitude. I think the TechPod science channel is probably going to correct me, because it's probably like more like 10 to the minus 35 seconds or something like that.
The other thing I wanted to mention here is that I got very strong when I pulled up this Google Docs document. I got very strong luminiferous ether vibes from the term quintessence. And I started thinking like maybe some of these teams of researchers need some like branding exercises. I guess you could say the same thing about dark energy, though.
Well, look, naming stuff is hard. We all know that. Sure. Here at Brad and Will Made a Tech Pod, a name that we came up with as a placeholder name and then accidentally published the podcast.
Yeah, oops.
The big question I have about all this stuff. So there were two interesting takeaways from this. One is that like the lower bound on when universal shrinking could start is like 100 million years from now, which, while a long time on a human scale, is relatively short on a cosmological scale. That means we could see a universal contraction before the end. The sun runs through its main course of fuel, and like. This is a novel like the idea that the universe could fundamentally change in the lifespan of our solar system is kind of novel to me. And I wonder, does universal contraction change things on a human scale? Like, do thermodynamics behave differently because things are getting closer to like what changes does anything change in the world 100 million years from now? Assuming we make it that far.
So this is, beyond my depth. But from what I've read from like Katie's work and some others, the short answer is no. Even if like the wildest kind of theories about this come true, it's still operating at a time scale where we'd all be dead. Like the human race would be gone, just because like even in the time scale you're talking about,
so like 6-7 months from now.
Yeah, we have to. we have to expand well beyond our solar system and to really even consider that a possibility. So I'm not willing to let climate change go to the next generation, but this one I am really willing to let go.
Okay, fair. This might be wildly oversimplified, but I mean, you're kind of talking about like basic tenets of physics changing as the nature and scale of space changes, right? But I mean, like space is expanding rapidly right now, and we're not, we don't.
I wouldn't think about it that way. I really think about it as like there's elements of our explanation of physics that we have put placeholders in because we don't have a full definition of what that is. And so we can call that physics is changing, but I think of it as more, it's like it's filling out. It's a more complete physics that's coming online as opposed to it's fundamentally changing in some way.
I don't have a good segue for the next one.
What is the next one?
I thought we'd talk about our friend. Human endurance is the topic of the day. I think here, it's making lots of small incremental changes, advancements in science over a long period of time.
Yeah. Why don't we? Hey, science happened in the past too. Why don't we look backwards for a bit instead of forwards? So this year, the wreck of the Endurance, which was the ship of the final major expedition to the Antarctic in the kind of, what is the formal term for that period in the kind of late 19th, early 20th century, the kind of heroic age of Antarctic exploration.
It was large men with dogs traversing impossible terrain.
A lot of European countries were funding expeditions to the Antarctic, probably for commercial and geopolitical reasons, if I had to guess. Because hey, it was a whole continent just sitting there waiting to be dominated.
It was anyway, a 4X game back then, Brad.
Yes. Anyway, I don't know if are you guys familiar with that expedition and Shackleton? Like he's a really kind of a amusing, larger than life figure. He was like a huge drinker, like apparently like an enormously charismatic kind of a womanizer, but like loved by all and sundry, though apparently like a very inspiring leader. Well, like in the final analysis, he led this expedition down there that never even made it to Antarctica and got stuck for 2 years and nobody died. He managed to engineer a rescue that saved all, I think it was 27 or maybe 28 men.
Mm-hmm. There are these incredible maps of the journey of where we think the Endurance went down and then the rescue boat where they had to like sail away and how they went onto land. And those maps are amazing because even you give me modern technology, I'm not sure I survived that trip.
Yeah, it's crazy. So essentially they sailed to Antarctica in the Endurance and it got mired in pack ice and was trapped for, I think it was 10 months, but, with various periods of drift happening. It got relatively close to Antarctica, but never actually made landfall. Eventually was so kind of crushed in the ice, in the movements of the ice, that it first started taking on a lot of water, and they had plenty of time to get all the supplies off, including, I'm sure, plenty of booze, and all of the something like 70 sled dogs they had with them, et cetera, et cetera. Eventually it did sink after it had taken on enough water. Yeah, I mean, this is not really germane to the discovery of the wreck, but he and a small number, so they made it to Elephant Island, established a base camp to try to survive. He and a small number of men took a whaling boat and sailed 800 miles to the closest human civilization.
Isn't a whaling boat like 30 feet, like a 30-foot long rowboat at that period?
That is my understanding. So like I know absolutely nothing about kind of maritime mechanics or whatever, but what I read about this is that trip in that whaling boat is considered like one of the most heroic episodes of naval or marine travel in history, essentially. Anyway, that's all fun. Also, another fun little side note, one of his previous expeditions down there, the campsite was discovered about 12 years ago. I think it was around 2010. They found one of his previous camps, and there were multiple intact cases of whiskey and brandy still there that were over 100 years old, buried in the ice. And there is actually, it's not amazing. I've had it. There is a recreation called Shackleton of the blended malt Scotch whiskey that was found at that base camp that is on the market. I don't know that I recommend it, but it's a fun side story. Anyway, let's get to the shipwreck. So yes, there have been multiple attempts to find the shipwreck over the last, say, 20 years, I think. I didn't find a lot of detail about why the one this year was finally the one that was successful. Although, Kishore, you pointed out that Saab, the car company, made the submersibles that were used in finding the wreck.
I love it. It's not the James Cameron like sitting a little like, Steve Zissou looking like submersible and going down to the wreck. It is Will, you remember going and seeing Open ROV at Maker Faire all those years?
Yeah, of course.
It's a scaled up version of that, is what this thing looks like. It is kind of a flat ROV that has a camera at the front. It's much larger than that Open ROV that, Dave Lang and Eric Stackable designed. But it's this kind of flat submersible that is just kind of maneuverable and has a big ass camera on it.
Box with propellers and instruments attached. I mean, that was Dave's whole thing when he pitched that to us, was like, hey, I wanted to make a cheap way to get instruments to the bottom of to underwater places, and it turns out it's a smart way to do it. Where did they find so I mean, I assume luck plays into this a fair amount. You just go down and start looking, right? Where you think it's likely.
They had predictions about where it had drifted to. And they were not exactly accurate, but it gave them obviously a search area. So it was found at the bottom of the Weddell Sea at a depth of almost 10,000 feet, which, like, I don't know a ton of shipwreck depths. I know the Titanic is, I think, around 6,000. 10,000 sounds extremely deep to me. There may be deeper ones out there, but that's very deep. The thing, well, there are a couple things that sort of fire the imagination about this story. The other one is the kind of tale of survival, but about the thing about the shipwreck to me that is so kind of marvelous is how remarkably well preserved it is. And there are a couple of thoughts. I mean, I'm sure this is still under study, but there are a couple of thoughts about why that is. Number one, it seems that cold water wrecks just tend to deteriorate more slowly than wrecks in warm water. But the bigger one here is that the scientists on the expedition have inferred that there are no wood-eating microorganisms at this depth and this low temperature at the bottom of the Antarctic like there are in warmer waters. So that thing, I mean, there's plenty of, very nice 4K footage out there of this thing. And it's kind of chilling almost to me, like, haha, pun intended. But like, it's I get a little like, you get chills looking at it because it is just sitting there intact on the bottom of the Antarctic. And like the lettering, I don't know if that's brass or whatever, but the endurance lettering on the hull is just there and like in excellent shape. I mean, it's really just kind of remarkable to watch.
I encourage people to watch the footage. Like on the life question. So scientists have been analyzing the footage because it was shot in 4K, as you mentioned, and there is a lot of life down there. And most of it is stuff that we would ascribe to as like filter feeders, and they're feeding on something we call marine snow. It is basically algae that die and like fall towards the bottom. And so there's a lot of stuff like starfish. They found a couple lobsters that kind of look like hermit crabs that kind of show up under a UV light. So there's it's teeming with life, but there isn't the kind of bacterial organisms that would digest wood. And there aren't the kind of currents that we'd expect at the bottom of the sea that would just physically rip it apart as well. The other thing is that the wreck is in a protected area, so you can't touch it. Like we can never, according to current law, we will never remove anything from it. So I know like people at the British Museum are sad they can't steal another thing to add to their museum, but it is just going to stay down there. And there's something about that is lovely to me. And there's something about this that is also sad because we should have never been able to find this. This is a story of climate change allowing us to find this ship.
This should have been under ice that we never could have gotten through, right?
That is a depressing aspect of this that I the fact that it is a protected historic site, it's under treaty. I mean, it's actual international agreement that has designated it as such. But if you compare it again to something like Titanic that has been repeatedly damaged by people exploring it, and like Cameron literally landed a submersible on the deck of the Titanic at one point while he was down there shooting it, and so that wreck has just been abused excessively by explorers. So like for this to sit there as a monument to this historical event and not be messed with is kind of beautiful in a way to me.
Well, and this is a wood hull ship too, right?
Yes.
So like the metal hull of the Titanic eventually was going to rust and go away. The fact that the wood has nothing eating it there means that this conceivably could be there for a really, really long time, which I think kind of lovely. Also, nobody died on it, which is a really refreshing change for most most shipwrecks, it turns out.
Yes.
Yeah. Oh, so we've talked a lot about science. I kind of think it's time to do a little science. So,
wow, that is a hell of a segue there.
So, Brad, in the show notes, there's a link to a Google Colab site, and there's a sequence that I want you to put into that site, and we'll kind of come back to it in a couple minutes, because I want to talk about AlphaFold and EMS fold, which I think are some of the most important developments in structural biology in a generation. AlphaFold is a product of DeepMind, Google offshoot. EMS Fold is a project of Meta. I'll get into the differences here in a second. First, a slight kind of oversimplification to talk about how important proteins are. So I'm on a tech pod, so I'm going to kind of like make a strained analogy here. So if we think of like DNA as physical memory, RNA kind of works as sort of the RAM of the system, and proteins are the software. They're the thing that like does all the work that results in the interfaces that actually meaningfully do stuff. So like protein functions, they make up antibodies, enzymes, structural report in cells, messengers. They transport molecules around our body. And the sequence of those proteins, which are made up of amino acids, and in humans, there's 20 common amino acids that make up those proteins. Their sequence determines their structure, and their structure determines their function. Now, when we talk about a system that has 20 amino acids, the length of a protein is basically, it could be infinite, but with 20 amino acids, so you just chain them together and that forms these proteins. The possible proteins you would consider would be like 20 to the n power, depending on the length. Essentially infinite. But because of constrained systems we live in, it's not infinite. There's finite, but it is a massive, massive number that we think is possible out there. And so determining the structure of these proteins, especially the ones that are known, are essential for us to unlock all sorts of information on how things operate in these systems. And right now, the way a lot of this is discovered is like we will get a protein, we'll actually like image it, like we'll make it like X-ray crystallography or, other methods, and basically say this is like the sequence of a protein and kind of work backwards. Well, these AI systems came in and essentially said, what if we can actually predict the structure of the proteins basically based off the sequences of proteins that are known and the shapes of proteins that are known. So AlphaFold a few years ago took on this idea of like, we're going to train on this shared database called the PDP. It's a protein structure database. And we're going to enter these competitions called CASP. These are annual novel protein prediction competitions that are hosted by academics every year.
And they're coming up with models to predict the proteins for these competitions?
Yeah, so AlphaFold came in with a AI model to essentially say, we're going to predict the protein. So what the competition would do is they would actually go through and develop do an X-ray crystallography on a protein, understand its structure, have the model try to predict its structure without telling them the information, and then compare the results at the end. It's a little more complicated than that, but like that's the basic idea. And so AlphaFold goes through a series of these competitions over the years and gets better and better and starts improving on the scale of these models. Last year, it essentially, this is CASP 14, so it might be a year and a half ago. There was no difference between the proteins in real life that we like image versus with the predicted structure from AlphaFold. And that was sort of heralded as like, holy crap, we got something here. Then this year, AlphaFold released a database of their predicted structures of 200 million proteins in the human body. And their kind of a theory of the case here is that those 200 million proteins, those are the known proteins, and those will be the limit of human proteins in the human body.
They think that's a complete set.
That is close to the complete set. And so I'm not a machine learning expert, so I'm going to kind of qualify this, but they use this system called a multi fold machine learning model versus Meta's EMS fold uses a transformer model, which is a natural language processing model. But anyway, so they essentially use this model to essentially map how the chemical bonds actually shape and form so that they're able to predict these structures. So, Brad, any chance that finished running?
It is, in fact.
So what I gave Brad, I gave him an input for a protein sequence, and he put it into AlphaFold and actually ran it. And the output of that Google Colab is that it shows you the structure of that protein and gives you a 3D rendering of it. If you scroll down.
Yes. Oh, it's actually literal 3D.
You can manipulate it and move it around
and zoom it.
So that sequence was hemoglobin, which I gave you. And so what you see on your screen is you just image the predicted sequence, the predicted structure from AlphaFold of hemoglobin. And hemoglobin is a well-imaged protein, as you can imagine. You can Google hemoglobin and compare it. And what you'll find is they're almost identical. The place that they're not identical is that proteins also don't just exist upon themselves. They interact with other cofactors, whether it be with other proteins or with other confounding elements. So in case of oxygen, in case of hemoglobin, there's oxygen and other cofactors that it's interacting with. And so the shape of hemoglobin that AlphaFold produces is super close. It's great for science, but it's not perfect because it doesn't model that interaction. And so beyond the AlphaFold releasing this database so that you can now query for a structure of protein and then go potentially make it, which accelerates the scientific process, scientists have been hacking AlphaFold. That was air quote. I realize that doesn't come through on podcasts.
Yeah, it's an audio podcast. Sure.
They've been hacking it, AlphaFold, to actually start to mimic how proteins interact as well. And so it's been fascinating how they're now taking AlphaFold and taking it to the next level. And so CASP 15 was just a few weeks ago, and AlphaFold actually didn't enter this year. But scientists who took AlphaFold and built upon it did enter, and they started to model how proteins interact. And it's showing just the reason I think this is a huge story is we now have a system of predicting structural biology in a way that we hadn't for years. And the level of acceleration that we're seeing in terms of how scientists are using this is accelerating really, really quickly, to the point now where scientists don't even have to guess a protein structure. They can query it, they can in a matter of minutes image it and create a predicted structure, and then go to the lab to actually do some of the work on the confounding factors and some of the hard work about sort of putting this into practice. Meta's work is very similar. EMS Fold predicted 600 million proteins because it was across multiple organisms. They use a natural language model, which isn't as accurate as AlphaFold because it isn't looking at sort of the geometry of the potential shapes of the actual compounds themselves. But from this transformer based machine learning model, you also get a much quicker response. So what takes 10 minutes from AlphaFold takes only a couple minutes from EMS Fold. So the amount of information that you can generate so that you can get to some of the experimental work is so fast now that it's just reshaping the entire landscape of how proteins work. This is the baseline work that we need to do to think about any development of drug targets, of disease modeling, mechanisms of how cells function and work. It's an incredible tool.
The interesting, I was gonna say the interesting thing about this is that understanding these connections and understanding how different things interact with it lets us derive better drugs and things like that can bind directly to protein sites because a lot for people who aren't biologists or don't remember their high school biology, proteins basically let you do let your cells do chemical reactions at lower temperatures than they would. Temperatures that won't kill you, basically. For all is the easiest way to describe it. It does a bunch of other stuff as well, but it does that by grabbing onto something and then the protein moves in some way that was ineffable and understandable until very recently, and now we have a model for that we can get in and look at, and it's really, really cool stuff.
It's fascinating. The people behind AlphaFold are on their way to a Nobel Prize. They won a breakthrough prize this year, which is generally a good sign that things are on the horizon for them. I will say one thing about EMS Fold that I think is really important is EMS Fold, very different model, because it's a natural language model. It really looks at sequences really well. It's going to help us look at mutations in proteins a little more efficiently than AlphaFold will. So while AlphaFold can really do incredible work on just the fundamental proteins that exist, you can go to a database called Uniprot, which is like a database of known protein sequences, pull out a sequence, plug it into AlphaFold. EMS is going to start to predict mutations in those proteins that'll help us attack a whole host of other biological diseases and issues.
Who owns this work, Kishore? Is this owned by the companies that do the models?
Who owns what? So the code is owned by AlphaFold, which is part of Alphabet. But the output is not. I mean, you're basically running a piece of software, and they don't claim proprietary ownership of the sequence that you put into it, nor the output, from what I understand.
Fascinating.
This the site you sent me is interesting. I don't know what the name is for this particular Google product that allows you to run code on some kind of cloud instance.
Oh, that's Google Colab. So you can basically create an instance and run all sorts of, there's all sorts of intersections to Google products and stuff. I've always used it for like cloud-based queries. But the fact that AlphaFold is built into Colab, so that like anyone can do it. You can just go to this website and input a sequence.
Yes, that was going to be my question, because you can go step by step down here and expand each step of the processing and you can literally look at the Python that it's running to process this stuff. So knowing that they set that up ahead of time is cool. I'm curious. I don't know that any of us could answer this, but like, I would love to know like what the hardware, the machine learning acceleration situation looks like for a lot of these research teams. Like, are they running like a lot of like custom high-end ASICs for this stuff, or do they just have like racks of off-the-shelf 4090s, or like I don't know.
It depends on their budget, Brad.
Yeah, I figured that was the case, but I guess the real question for me is, are they kind of limited for budgetary reasons, primarily probably to consumer hardware, or are there like much higher end, like high performance computing kind of solutions out there for stuff like that? I mean, obviously Google has deep pockets, so I'm sure this effort is fairly well funded.
I think much has been written about this, but I have not perused this myself. So I don't know, but I bet you we could find out.
So Kishore, we know some people who run labs that do a little bit of this kind of work, and they do a mixture of cloud and local compute depending on what they want. Generally, my understanding is that if you have the budget to do cloud stuff and you want faster results, you might see faster results. But if you have enough data to make keep a big workstation with 20 GPUs and it constantly running, then it behooves you to do both. Keish, how are you doing on time? Do we have time to do a couple more? Or are you okay? Do we want to talk about DART next?
Yeah. Let's dart to the next topic.
Oh boy,
NASA's double asteroid redirection test, which the culminating event of which took place, I believe, on September 26th of this year. DART was conducted by NASA's Planetary Defense Coordination Office, which is about as sci-fi a division sounding name.
I assume that's like three people sitting in a closet somewhere in like an off-brand NASA campus someplace that they don't let them out very much.
No way. I believe it's at I think headquarters for the planetary office is in DC, but a lot of the work is run out of JPL. So if you consider Pasadena low rent.
Okay. No, Pasadena's nice. We like Pasadena. We're friends with people from Pasadena, but it's still three people,
no,
right?
It's actually quite a large project. This is really out of the Near Earth Object Observations Program. And it's one of those programs at NASA where they grant out money. So there's people that work in-house, but also like associated people out in the world too, that are funded to work on stuff. And they are just looking for stuff that might hit us or come close to us.
I feel better knowing that they're there then.
So this was an attempt to test one method of diverting the trajectory of an asteroid that might collide with the Earth. And in this case, they did that by literally slamming a spacecraft head on at the exact opposite direction of the travel of the asteroid. They chose.
Did it work?
Yeah. What's that?
Did it work?
Yeah, it worked. So they reported results, I think, about a month after the impact or even less, and said, yes, it worked. Their threshold for success was to, I'm looking for the figure, they considered altering the asteroid's orbital period by at least, I believe it was 73 seconds to be the threshold of success, and they actually altered it by about 32 minutes, give or take. So, by NASA's own reckoning, this thing was a resounding success.
Long history of under-promising and over-delivering.
They chose an asteroid called Dimorphos, which is itself a satellite of a larger asteroid called Didymos, I assume is how this is pronounced. Either of those were considered an imminent threat, but it was a good test subject for this. The craft slammed into the asteroid at about 14,000 miles per hour. They didn't load it up with really any kind of scientific experiments or payload other than what was required to get it there and a camera. So you can go on Wikipedia or on NASA's site, and there's like a great succession of images of just closer and closer to this giant rock. And then you can see the very final image before it's slammed into it right above the ground, which is fun. It did have a piggyback kind of secondary satellite that detached a couple weeks before the impact and acted as sort of a cameraman to record the impact and see what happened from a distance there. So yeah, like that's kind of the gist of it, is that they have determined this to be, I guess, a fairly effective strategy. They just literally yesterday, at the time of this recording, put out another release about some analysis of the results. So, as you might expect, it ejected massive amounts of material when it impacted. I think they said about 2 million pounds of rock were ejected from the asteroid, and they have determined so far that the force of the ejecta altered the travel of the asteroid far, far more than the actual force of the impact of the spacecraft. Like I think they said that it amplified the alteration by like 3.6 times.
So you're saying that the deep impact of the rocket stopped Armageddon?
Sure.
So
that sounds right.
They imaged it from everywhere. So like JWST was pointing at this, Hubble was pointing at this. Like they basically were like, what if we just point every telescope we can at this thing to image the actual impact and the resultant stuff. And those are beautiful to look at too. This isn't the only way we can move asteroids. We can do things like gravity tugs, where we put something right next to the asteroid and slightly tug on it using the gravity of the other object, and you can just change the trajectory without having to smack it. But this is the most American way to change the trajectory of an asteroid.
No. This is the second most American way. The most American way is to put Bruce Willis up there and give him a big drill and a nuclear bomb.
Yeah, until there are nukes involved, I'm going to say it could get even more American.
Is this a rocky metallic asteroid? Or is it a dusty asteroid? Do we know?
It's rocky. There is like some definite like regolith on it, so it has. I can't remember what the composition was, but it is a rocky asteroid.
It's not like a hard iron nickel asteroid.
I don't believe so. I saw it was described as a rubble pile at one point, colloquially, if that tells you anything.
The pictures, like watching this happen live, is one of the wonders of the modern age moments this year for me. Like you had a live feed of images coming in every couple of seconds from the cameraman, and then also the live feed of the images coming in from the probe as it was about to impact. And the last shot you see looks like it's from about 5 feet off the ground, and it has incredible definition of the rocks and the shadows and the surface of this asteroid. And then you get like a partial frame on the next one, because
the top 10% of the image filled in before it impacted.
Yeah,
it's fun. Yeah,
it's pretty amazing.
I'm glad you mentioned the gravitational tug, because I had always heard that was kind of the most plausible or promising method of doing this. And there's something kind of like beautiful and elegant about it to me. You know, you could do this without destroying things, but yes, of course, we just.
Well, but also the fact that the ejecta, I mean, of course, the equal opposite reaction, all that energy has to go somewhere. So it makes sense that hitting it really hard with something is going to make something come out the other side and slow it down even more. So that's cool.
Also, maybe not surprising to know that the ejecta has now assumed a kind of comet-like trail or tail form subsequently. So there's that.
I'm just excited because it's the kind of thing that like seems like it would be really hard to get funding for people who won't fund climate change work. When, you know, we it's one in every 65 to 100 million years. So we probably have a little bit of time left. We don't need to spend money on this right now. We could wait until later. It'll probably be fine.
Yeah. Real quick, I want to jump in here. Speaking of the last giant impact, did you see the story from earlier in the year? I just came across it last night that the Tanis dig site in, I want to say it's like South Dakota. Which state is Tanis? North Dakota. Claims, this has not really fully been vetted. There are certainly people in different disciplines who seem still a bit skeptical about this. Claims that they found fossils of animals from the day of the impact of the
big one.
Yeah. How do you pronounce the impact site? Chicxulub?
Yeah, Chicxulub. Or I'm not pronouncing that right.
I believe. I've never heard it said out loud, but yes, the asteroid that wiped out the dinosaurs. Like this dig claims to have found parts of animals, fish fossils with all kinds of telltale geologic evidence of having been exposed to the factors on the day of the impact. Again, this is still under study.
How would they know down to the day? That seems.
Well, they had a calendar and, you know, it's like, hey, there's a big X and then the day before is circled and then that day is not circled. So, you know, it's just process of elimination.
Who knows if it's maybe the next day, but it's mainly analysis of traces of geologic material. Like they found the kind of glass spheroids in the gills of the fish that contain traces of, I don't know if you're familiar with the boundary in the geologic record.
We're talking KT boundary time. Yeah.
Yes. So I found out last night that apparently the term KT boundary is no longer in fashion. Now it's the KPG boundary.
Oh.
It's for Paleogene rather than tertiary. So it's now the Cretaceous Paleogene boundary. Anyway, what is it? There's like a tiny layer of iridium around the entire world at the point where the impact occurred. Anyway, they look for traces like that primarily in these fossils and are surmising that these animals were exposed to the direct effects of the impact.
Look, Brad, some fish just like to huff indium lined glass beads. You can't stop them. They're just going to get them in their gills. Nothing can stop that. Should we talk about, real quick about fusion? Because that was the news this week. The NIF, which is, I think I foolishly didn't write down what the acronym is.
National Ignition Facility.
Thank you. I thought that's what it was, but I wasn't sure. Shot a couple weeks ago, shot 192 laser beams at a tiny, tiny little target filled with fuel and achieved fusion ignition in a controlled setting for the first time on Earth, which is very exciting.
This is inertial confinement fusion, which is not plasma controlled fusion, which is bound in a tokamak, which is different. But
the plasma confused fusion is the thing I always think of as the torus shaped reactor with the plasma floating in, and like it powers the impulse engines on the Enterprise is all I know. I
magnetic donut.
Yeah, exactly.
Correct. Tokamaks power the engine in the Enterprise. NIF was the location for the Star Trek 2009 engineering room. They actually shot. That's where they shot.
Really?
The engineering.
Oh,
yeah.
No kidding.
I thought that was a Budweiser brewery.
The pipes are different.
Really,
this is like you can see elements of engineering though in that 2009 Star Trek.
I'm Googling pictures of this right now. That's cool.
So yeah, the fuel target was about the size of a peppercorn. It's enclosed in a really cool diamond shell that's almost perfect, as perfectly round as we can make it. It seems like it has just a tiny little tube through that they can feed the fuel in. The laser put in 2.05 megajoules of energy into the fuel. The reaction produced about 3.15 megajoules of energy. So this is the big deal. We put some energy in and we got more energy out because of the fusion reaction happening. Now, there's an asterisk because, of course, the lasers are pretty inefficient. So getting the lasers to produce 2.05 megajoules of energy required about 300 megajoules from the grid. So we have look, there's work to do. Some optimizations. Is the takeaway here. Yeah, some optimizations.
Do we need to very quickly define fusion? Fusion is kind of the other nuclear process by which energy can be released.
Yeah, it's the one we're all most familiar with because it happens in the sun every single moment of every day.
So all nuclear power plants operate on fission, which is splitting atoms, which produces a lot of waste. Fusion, less waste, much more efficient is what
essentially
happens in the
no
sun.
waste, because you're basically taking hydrogen, fusing it together and forming helium. We don't go beyond that. We don't have the ability to have helium form higher energy compounds, but that's the fusion that we're talking about here. And it's not just about ignition, which is initial fusion, but actually sustaining that fusion for some period of time. And so this fusion actually lasted, close to a few seconds to produce that much energy.
Which is a long time.
And the way it produces energy is like how every kind of reactor at scale works, is basically it generates a ton of heat. In this case, it emits a ton of neutrons. Those neutrons will go get absorbed into something like a heating jacket or something. And that thing gets hot. And then we use that to like heat water to generate steam, and that'll spin a turbine or something, and that'll generate energy.
So, I mean, the upshot is this is a process, like work on fusion has been going on now for 70 years. We started in the 50s, I think. It's been a bunch of tiny iterative steps, but this is a kind of a big milestone along the way. It feels like to me. I'm not a fusion expert. The further journey from here into SimCity style fusion power plants that let us all get free of fossil fuels forever and run clean hydrogen, helium producing power plants. It seems like there's still lots more work to come in the future, right?
Yeah, I would say my friend Kyle Hill, who's a science YouTuber, kind of put it in this way that I think is easy to understand. There's like 4 milestones we really have to hit here. One is just to achieve ignition at all, have fusion happen at all, even if it's energy, like a net energy negative. Then there's what happened yesterday, which is achieving net energy positive, where some of the energy we put in from the lasers, in this case, we produce more energy out. Then there's the next step, which is the energy of the system put in is less than the energy that comes out, which means like handling all of the 300 megajoules coming from that fed from the grid into these laser lamps.
Well, and presumably like making the fuel and stuff like that too,
so that's all part of that milestone. And then the 4th milestone is actually building a system around all of this to actually generate power. So all of those steps, you need higher and higher energy. And for the most part, from like the 50s through, I would say like the early 2000s, the energy increase that we're seeing along the scale was following kind of a Moore's law kind of axis of gain. And then it slowed down in the 2000s as we had to build like bigger and bigger systems to actually generate the kind of energy output. Like you go to NIF, like the 192 lasers, they are the most old school lasers you've seen. They're built with these flash lamps, these giant tubes. They're like freaking 2 feet long tubes, and there are hundreds of them that flash. And then the light pulse that's sort of generated goes through these concentrators to make a laser. A laser pen that we have in our like hip pocket over the side has somewhat more advanced technology than those flash lamps do. That's a bit of an extreme here, but I just want to acknowledge like these systems were built with old technology. So there are efficiencies that will come from building more modern systems here that'll help balance that equation, but we still have a long way to go. So the ratio of energies is oftentimes referred to as Q. So the energy in versus energy out. So that we got to Q1 here. We need to get to something close to Q10 to have a viable a ratio to build a power generation system.
And that's what the goal of the ITER project is in southern France, that the US and the EU and China and I can't remember what the other 2 countries are.
It's 35 countries. It's a huge project. There's actually I think there's 12 tokamaks coming online in the next 15 to 20 years. So this isn't a small scale situation where we're relying just on one project. But ITER is the largest one. We've never achieved ignition with a tokamak. So there's a lot to prove with that technology where we're using magnetic fields that are 300 times as powerful as the magnetic field of Earth to confine plasma to force the kind of pressure to achieve that fusion. But there is a lot of hope based off of the science that is the more legitimate pathway to power generation, even though it's decades off. NIF, to be cynical just for a second, basically allowed us to put a little bit of deuterium and tritium, isotopes of hydrogen, in the middle of this and shoot a bunch of lasers on it and test the output. Well, what other radioactive materials could we put into a target and test in a facility without actually exploding it? You'd almost think a nuclear weapons facility would be really interested in that kind of technology. And guess what Lawrence Livermore National Laboratory does? So there is some military purposes to this, about testing fuel. So I wouldn't think about NIF as like the project that gets us to a power plant, because the system that it's designed, like you shoot a target, this Hall-ROM as it's called, to generate the energy. Now you have to, even if that proves viable, now we have to design a system where like a Hall-ROM like perfectly falls into place and we shoot it with all these lasers and ignites, and then another one falls into place and shoots and ignites. And that has to happen like every less than a second. Like you can imagine all the failures in like dropping a pellet perfectly into a line of lasers.
It's just a burp gun of ping pong balls going through a giant laser cannon. Yeah.
I remember first going to NIF. I went to the facility in like 2009 and they had like an animation of that. And I laughed out loud. I was like, come on. Enough with that. I understand the point of this system, but stop joking around with that being a viable way of producing a power plant. That being said, this is an incredible milestone just to get to Q1. And so the fact that we're seeing progress and hopefully seeing progress in the tokamaks over the next 10 years is something to celebrate.
Is it an oversimplification to suggest that once fusion is stably and efficiently achieved, that it's the end of the world's energy problems? I mean, is there even a need for diversification? Like kind of solar, like orbital solar collectors and stuff like that, or is that the holy grail, or is it more complicated than that?
I don't want to say it's the end, because like tritium costs like $30,000 a gram right now. So it's not like a cheap fuel. So we have to come up with ways to generate the fuel that's actually appropriate for these facilities. But if you could do that, there's enough like hydrogen in like a cup of water to power your house for a year with fusion technology. So we get into the place where the energy output isn't the issue anymore. It is finding the fuel, and it has no emission for all intents and purposes.
Yeah, I mean, the only thing that's bad is the neutrons eventually make the cladding for the reactor a little hot, but like compared to what comes out of a fission reactor, it's basically nothing, right?
Yeah, you turn off the input to a fusion reactor, fusion stops.
Yeah, turns out that's nice. It's a good thing. Kishore, thank you so much for coming by. It's always nice to have a visit that's not about the impending apocalypse due to a virus. So we'll have to do this again sometime. I have one more kind of general question for you, and you may not be the person to answer this, so I apologize in advance. But like all of the stuff we talked about today are all kind of application science. We don't talk a lot about theoretical science in general, much less the popular science conversation world. And like all of this work is based on decades of theoretical research that it seems like as a country we don't really do very much anymore. Often we spend all of our money and time and energy on applications for things we've already figured out, and there's a little bit less on the actually, hey, what happens if we do this, and how does this part of the world work in a way that may not have any kind of long-term application?
I mean, my short answer is, like, first and foremost, we talked about quintessence for a while, which is not a word that you're basically asking, like, are basic research like and its value to the larger kind of ecosystem of people, and talking about that more. Storytelling about basic research is hard because we are naturally inclined to say, like, what does this mean? Why does it matter? How does it relate to like my life? And basic research essentially is, in its purest form, is curiosity driven. And like, we don't have any connection outside of like increasing the body of knowledge without any like overly prescribed notions of where that kind of goes. We still invest a ton of money in basic research from just a pure money standpoint. It's just that the amount of money as percentage of our GDP has fallen since the since the 50s and 60s. So we're not investing nearly as much as we used to. A number of other countries are investing a lot more. I think the success of basic research is in everything that we use, our phones to on down the line. Like the nature of technology that's in Hubble is in each of our smartphones is kind of a ubiquitous concept now. So we don't know what we can achieve from all of this. But I think by telling the stories far enough on the pipeline that it can capture the imagination, gives people insight that there's all this work that has to come before it to get to that point. And it's important to support that endeavor, as opposed to just looking at the pure application. And I think talking about projects like AlphaFold, which actually doesn't do anything on its own, it's a tool to enable that kind of work, helps tell that story more. And I think that's what that's the opportunity space, is to tell more stories with the underpinning of all of that work. I mean, so much of when I listen to FOSSPod, is like, that's the story of FOSSPod to me. It's like all of these technologies that enable the technologies that we use every day.
Jeremy Allison described it as the plumbing, as he builds the plumbing of the internet. And I think that's maybe the most apt.
And it's the same thing here with science.
So, and just so people have an idea of scale, like our funding in the US for science in general is almost infinitesimal compared to the money we spend on other things like military budget and stuff like that. Right. So we're not talking about a ton of money. We
are still talking about billions of dollars, though. So it's not nothing either.
Of course. But billions of dollars compared to, it's not like we're buying a fighter jet that cost a few $1 billion. Anyway, I guess that'll wrap it up for us this week. Kishore, thank you so much for coming by. Where can people find you and find out more about you in a what I assume is a post-Twitter world by now?
One can hope that it's a post-Twitter world. I have stopped podcasting. This is the first time in 10 years I haven't had a podcast. And my wife put it to me this way: the people will be okay. And I was like, wow. That's rough, but also accurate. You can find me places.
But where will people find out what you think about the latest MCU movies? How will they know what you think, Kishore?
You can find me on the TechPod Discord. I'm also in Will's Discord. You can find me places if you need to find me, and I will espouse you with all of my thoughts about where the MCU has lost its way and why Andor is the best Star Wars in a generation. But I will say I am going to post some my top 10 science stories of the year, like written narrative pieces, and my top 5 science books of the year in the Discord as well. So check that out. It should post by the time the episode drops. So I encourage people to check it out, because there's great books and narrative pieces on science that can help for this exploration. And I'll probably just continue talking even after you guys hop off the line, because that's the only way to podcast now for me.
Thanks, Kishore. That'll do it for us this week. As always, the Tech Pod is a 100% listener supported podcast. So if you would like to support the show, you can find out how by going to patreon.com/techpod. Thank you, supporters, patrons.
Yes, thank you very much. Nice to see you all.
As always, a very special thank you to our executive producer tier patrons, including Nick Johnston, Paddle Creek Games makers of Fractured Veil, Andrew Solosky, Buddy Thorpe, Stay Healthy Crimes. I like that one. Just Wedge, Joel Krauska, Teal, not that one, and James Kamek. Thank you all so much.
My God.
I hope everybody, I don't know where you are, but where we are, COVID cases are spiking again. RSV cases and flu cases are spiking. So go get your flu shots.
Yes.
Wear a mask. Be safe out there.
It's rough out there.
Don't get sick at Christmas, because that sucks, or the holiday season in general. And we will be back next week with another episode of the Tech Pod. See y'all then.